I've seen lots of different stuff cached, including things like SQL Alchemy database models, which have connections to databases, which is kind of a strange thing to serialize. I've seen people put connections to memcache in memcache, which is also kind of a weird one. And basically anything that you can serialize can go in. So a good use of memcache would be serializing some data structure to JSON and stuffing it in memcache. But maybe a more questionable usage of memcache would be using Python's pickle module to sort of serialize an object, which then knows how to deserialize itself using some code, which sounds neat when you first think about it, and then you realize that that could be an astonishingly bad idea, especially if you do a code upgrade and the code changes, or some model definition changes in your code, and you try to pull stuff out of memcache, and all of a sudden the things in memcache don't fit the things that you find in your code. And memcache doesn't let you enumerate the keys in memcache. So if you pollute a cache like I just described, it can be difficult without bumping the entire cache to figure out what stuff you need to replace or dump from the cache. It also makes exceeding your failover capacity incredibly easy. The whole idea behind memcache is to reduce load on critical pieces of your infrastructure. But if memcache goes down, if you lose access to your memcache cluster, what are you going to do with the additional web and database load? You basically trade off having a speed enhancement and load reduction by introducing a point of failure. So if memcache decreases, basically a memcache average will increase your load proportional to what it removed. And it can cause cascading failures. So memcache goes down, and all of a sudden you have what were 2 or 3 millisecond lookups taking half a second on your database. You will quickly introduce additional load into the database, and could essentially bring down your database cluster as well, in which case you're in a really bad spot and can't serve any traffic. So the solution to this is to build in emergency capacity. It doesn't have to be proportional to your actual memcache offload, but it should be enough to sort of deal with an outage before it gets to a bad point, and to be able to just turn off or isolate expensive features. I know on Yelp, if things go really badly, we can turn off a lot of auxiliary things, like we have a talk section. We can turn off like member search and stuff. And when all else fails, have an emergency maintenance mode, so you don't cause fires in the data center. Let's talk about data centers. Yelp, we're still a smaller company. We certainly don't have anything on the scale of Google's data centers, but we have 2 data centers in the U.S., one in San Francisco and one in Virginia. And adding more data centers, basically having one data center is fine, but at a certain point, you just can't really get bits to the rest of the world fast enough. So having another data center lets you increase capacity while also letting you speed up traffic for different geographic destinations.
Right. Do you have a lot of users out of the U.S.?
Sorry?
Do you have a lot of users out of the U.S.?
We have a fair number. We're expanding internationally. Yelp started in San Francisco and has been taking more of a community-based approach to its expansion. So, like I think I mentioned earlier, we've got a community manager here, Kara, who's responsible for basically growing the Cleveland community. We've been doing that a lot across the U.S., which basically bootstrapped most of our user base. And now that we're expanding internationally, we're starting to do the same thing. So our domestic traffic greatly outweighs our international traffic, but we do have a fair number of international users. Does that answer your question?
Are any particular countries that are continental? France, UK?
I mean, UK's been big for a while. That was sort of the next logical leap. We have a lot of Yelpers in Canada as well. I mean, a lot of European countries are still bootstrapping. We just launched in Singapore, which is our first sort of major expansion to the west side of San Francisco. So, yeah. Cool. So yeah, having geographic distribution helps you sort of mitigate the speed of light. I mean, the speed of light is not the limiting factor in most of our content delivery, but it definitely helps to be closer. But you introduce additional replication problems. You get, basically, it's important to keep memcache in sync. Having out-of-sync caches can be somewhat problematic. So you have to all of a sudden sort of replicate at least some subset of your memcache traffic. You have to deploy code across the country, which can be non-trivial, making sure that basically dealing with separate deployments of machines and different code versions can get interesting. And you start to see non-trivial replication delay. Getting 3,000 miles across the country actually does take a fair amount of time, especially when you've got sort of shuttling lots of data across. This is where you start to get into really problematic replication delay, things on the orders of a dozen seconds or more under heavy load. But fortunately, there are some solutions. You basically, for each data center you have, if you're using a replicated MySQL scheme like we are, you basically have a write master, which is only one data center still has the one true write master, which actually takes the writes. And so if you're say in our Virginia data center, if you had a real write to do, your web server might tunnel across the country to our primary data center in San Francisco and do the write there. But each data center has a write master which replicates writes from the true write master, but acts like a local write master. So that way you only have to replicate writes once between data centers, and then each write master then delegates writes to its read slaves within the data center. And you can actually take advantage of MySQL's replication stream if you use something like a black hole table to replicate memcache writes. I mean, you have to sort of add some sugar on top to make it work as expected, but you've already got one replication stream going across the country. There's no reason to try to set up a second one yourself. So that's most of what I've got on the back end stuff. Does anybody have any questions about what we've talked about so far on the back end?
I was going to ask about memcache and validation. So you're kind of, and you just hit it there, so you're kind of piggybacking on top of MySQL replication.
Yeah. Basically, the idea is you can use like a black hole table and then just issue some sort of semantic, like some query with semantic meaning to your write master, and then watch it replicate across the country, and then have something watching the replication stream in your other data center. And it knows the semantic meaning of the query that came in, and just extracts the key and validates it.
You guys have like a write-up on how you do that?
I don't, because I'm actually not all that familiar with that system. But it would probably make for a good write-up. Yeah. Cool. Any other questions?
I take it your web farm is virtualized?
No. So Yelp started in 2004, which is why I mentioned that we did basically we're built right up against Mod Python. And this was before we really had the benefit of things like EC2 or lots of cloud hosting providers. I mean, they existed, but it was definitely easier to get your hands on your own hardware. And then, so that's what we did. We basically have all of our hardware in-house. I think the only thing that we use a cloud provider for is a lot of our offline like MapReduce processing for lots of our log data and stuff. And we use Amazon's EMR service for that. But yeah, otherwise all of our hardware is in-house. Cool. Well, I have time for questions at the end too, so feel free to. We're going to talk about front-end performance. This is the best front-end performance cat that I could find. So there are a lot of front-end performance hacks that people have been doing for years, and there are probably more than I have time to enumerate here, so I'm just going to cover some of the big ones. But they're sort of guided by three principles, which is reduce the number of connections you have to make in HTTP route steps. Those tend to dominate a lot of basically negotiating an HTTP connection tends to take up a lot of the time of actually getting an asset, especially with things like broadband internet connections. Reduce download sizes. It always helps to have smaller assets if you can get away with it. And don't do things that browsers don't like. So I think maybe the biggest and easiest win that you can get for front-end performance is just to stick a CDN on it. CDNs are essentially, they're stands for Content Delivery Network, and it's really good at serving static assets really fast. Some examples of this that you may have heard of are Akamai. Amazon has one called CloudFront, Pretendo, and there are numerous other ones. They're massive. I think Akamai's at over 100,000 edge nodes at this point, which is a lot of computers. And they're geographically distributed, which is why they can get so fast. We probably have at least a couple edge nodes here in Cleveland. So if you use Yelp, you'll probably get the content, a lot of our static content from a data center somewhere in Cleveland instead of San Francisco. It's easy to set up and drop in. Basically, you just change your host name to a CDN host name that you just set up. And the CDN downloads your content once, and then will continue to serve it until you either invalidate it or you ask for different content. And it lets you lower bandwidth costs. Typically, bandwidth from a CDN is a little cheaper than self-hosted bandwidth, and it lets you reduce the size of clusters that you would need to serve static assets. Subdomain sharding. So the HTTP 1.1 spec says that a single user client should not maintain more than 2 connections with any server or proxy. Does anybody have any guesses at how many connections your browser actually keeps open with any single server or proxy?
5.
There's anywhere between 2 and 8, depending on what browser you use. This is probably somewhat out of date. I took it from a Stack Overflow question. But basically, that's being thrown out the window in favor of actual, real-world performance measurements. So this is pretty good. This will get us quite a fair bit of the way. But most users at this point have a pretty big pipe going into their home, big enough anyway. And being able to do more HTTP connections in parallel, if you can handle it, is usually a benefit. So the idea here is essentially if you've got some subdomain that you use to store your assets, maybe we have media.yelp.com, essentially just CNAME a whole bunch of other host names to that one. So we did this with medias 1 through 4.yelp.com, and then you essentially distribute your references to your assets. So maybe our JavaScript is served off of media 3, and some of our CSS is media 2, and then some of our images are media 1. And the idea here is to trick the browser into thinking you're connecting to 4 distinct locations to take advantage of up to like 32 connections at once. Caching is a huge one. You can this basically lets you eliminate a whole bunch of round trips by letting the browser hold onto your assets for as long as it can. I think probably the most effective or standards compliant way to do this at this time, at least from what I was able to find, is usage of cache control headers. HTTP has a number of cache mechanisms to make this easy. A big one is expires, but I think cache control tends to be overridden in favor of expires. There are 2 other ones called etag and if modified since, which you may have seen, which essentially send a hash or a timestamp with an asset when you download it the first time, and then on subsequent requests, your browser says, hey, does your hash match this one, or hey, has this thing being modified since this timestamp? And those are good mechanisms, but they still require an HTTP lookup. I mean, you have to initiate a connection and start talking to a server to figure out if things have changed. And it's usually much better to just say, hold on to this asset for 10 years, and go from there. But of course, if you ask your browser to hold on for 10 years, you could get stale things if you want to do something awful like update your assets. So a way around this is basically to version the assets using either a URL path or query parameters. So this would be like a sample request for some JavaScript file. So this is the response from the server. It has a cache control header with a max age of approximately 10 years. So you can, we put this one in here in case we want to bump all of the assets on the website. We can just change that with some global identifier if we need to do like a hard invalidation of the cache. And then maybe some hash of the asset, which changes when the asset does, but otherwise is relatively static. And then basically you just serve URLs like this, and when you want to invalidate the assets, you just change the hash and re-download an asset. And presumably the cached assets from years past will be invalidated at some point. Cookieless domains is a big one. This violates like everything they teach you about writing presentations everywhere. But I'm doing it to make a point. Like I just took this from my browser so you can see all of my recent locations and stuff. But this is what getting Yelp.com looks like. And so we've got some regular kind of headers here, stuff that tells what the user agent is, what kind of content we'll accept, what kind of encoding, what sort of cache parameters you want to use. And then we have this big header called cookie. And it takes up more than half the screen. And this is huge. I mean, this is necessary because our web app wants to know what cookies you have so we can sort of change content based on what we think you've been doing. But that's enormous. So this is maybe acceptable for getting Yelp.com, but that's a 2K overhead for the HTTP headers. And for static assets, I mean, a lot of your static assets will be under 2K in size. So having your HTTP headers the same size or even bigger than your static assets is not great. That's a lot of wasted bandwidth. So the idea here is that you essentially get a new domain or change how you assign your cookies so that you only send cookies to things that need it, and simple HTTP web servers that are just serving your static content don't care what cookies you have, so don't send them. There's some other assorted front-end tips. gzip is powerful. It's really great to compress your content. A lot of browsers support undeflating content when it comes in. There's some tried and true methods here, like always style sheets in the head, scripts at the end of the body. Avoid inline styles. Manipulating the DOM can be really expensive and can trigger a lot of browser repaints, which are, if you're doing it constantly, can be bad for user experience. And use Ajax to load non-critical content. If you've used Yelp and are a user, we have lots of things on the page that load via Ajax because they're simply not mission critical to have first. So that's what I've got on front end. I don't know how much time I have, but I'm just going to power through to the monitoring stuff. So this is a cat that is monitoring a bird that's going to be ready to pounce. So there's a couple kinds. So monitoring is really important and is something that's often overlooked until you get into industry or until it's too late. It frequently is a mission critical part of your application. You really want to build simple, easy to understand components because they end up being the most durable. And it's when your application is failing and you don't know why you can't get to the website, you want to know about it, and monitoring lets you do that quickly. Monitoring depends, the way that you monitor your application obviously depends a lot upon your application requirements and what your app does. Drop-in products are great, but usually they only get you so far. It's important, like I said, because it can tell you what's broken, and even if things aren't broken, it can tell you how well things are working, which might surprise you. So our strategy for monitoring is basically, we have three sorts of categories of monitoring tools. Alerts, things that page people in the middle of the night when hard drives are on fire or whatever. We use performance and availability analysis by essentially graphing the hell out of everything. And we have some tertiary tools which tell us a little bit about how our website is usable from other parts of the country or across the pond, and Ganglia, which is a classic another classic sort of graphing and monitoring tool for clusters of machines. So we use Nagios. Who here's heard of Nagios? Yeah, it's basically a piece of software that lets you write alerts and do either self-reporting or active reporting to check on systems. And it's really good for sort of binary. I mean, it's an oversimplification, but it's really good for sort of binary alerts. So whether or not something is okay or not. And when things aren't okay, it's really good at being really loud. So, I mean, we use Nagios. That's sort of really good for well-understood problems. Really easy to plug into systems to tell if load gets high, or we run out of disk space, or all of a sudden we're swapping, things like that. So this is I consider this to be sort of the easier side of the monitoring. I think the more interesting part is monitoring performance and availability. So as I mentioned earlier, we use a tool called Firefly for this. And another tool called StatMonster, which are sort of very tightly connected. Firefly we've open sourced. It's basically a graphical front end to time series data. If you've ever been on Brian's Stack, one of the organizer's website, he has an instance of Firefly running there if you want to try it out. It has a nice sort of extensible data ingestion API, so you can sort of throw data at it and it will create pretty time series graphs for you. And then we use StatMonster, which we haven't open sourced yet, one day in the future. But it's basically our data collection and pre-processing framework. It essentially turns log lines into statistics, analyzes those statistics and computes derivative statistics, and then stores them in an on-disk data format, which we can feed to Firefly. So a quick aside here, like I said, monitoring is often overlooked, and so is logging. I mean, everybody here has probably used print statements for debugging at one point or another, right? Like, what does this variable look like now, and what does it look like now? And logging tends to be essentially the grown-up version of print statement debugging. It's important because it's easy to, especially with websites, it's easy to ship with production code, and it's often the only source of information you have when things are going wrong. It's possible, but it tends to be very difficult to break open a Python debugger or GDB on a web server, like in the middle of a web request, to figure out what's going on. And needless to say, that'll cause whatever user initiated that request to be pretty unhappy. So we use logging for everything from sort of human readable stuff to as like a diagnostic tool to essentially storing ephemeral data as it happens. We use this to log performance data. We use it to log actions that happen on the website. We use it to log pretty much anything and everything. And so we log a huge amount of data. So much that we set up special infrastructure to collect these logs. I mean, it's not sufficient to just log things to disk anymore and then aggregate them offline. We use a tool called Scribe from Facebook, which is their open source log aggregation system. It's composed of essentially leaf and aggregator nodes. So you have a whole bunch of leaf nodes that are collecting log lines from web servers, and then aggregators which talk to the leaf nodes and associate lines based on the channel that we're written to, which is, you can sort of think of as like a file. And it's important to note that this is an eventually consistent system. So lines can be out of order or delayed, or in bad cases maybe not show up at all. So it's very much best effort. This is what a typical Scribe setup kind of looks like. You've got a bunch of web servers that are emitting log lines with certain channels. They hit a leaf node. The leaf node sort of collects it and says, okay, I know about this. And then occasionally an aggregator comes along and says, hey, what do you know about channel 1 or channel 3? And then the leaf node ships off its logs to it. Then the aggregators sort of make that into a coherent kind of file-like stream. And once you've collected, a day or an hour or whatever your log granularity is, that you can ship it off to the internet or local consumers. Or the thing I left out here is you can actually have local consumers tail a log in real time as if it was like a file-on-file system. So this is what our our monitoring setup roughly looks like. We've got Scribe, which is emitting log lines. We have this log digestion and stat aggregation component there. Essentially tails lines in real time. And then runs user scripts that we've exposed to other developers. Basically runs lines through them and emits statistics. So some unique key, like this is the performance for the home page. Here's how long it took. Yeah, Nick, you had a
Do
question?
you have any Splunk-like capabilities there in terms of like free text queries or digestion of the logs at a query level of the aggregated log set?
Not really.
Okay.
We do a lot of like offline log processing and MapReduce,
Okay.
but that isn't really query-like. I mean, we write MapReduce jobs to figure out something, so it's in essence a kind of query, but kind of a static one, and nothing really real time.
Okay.
So we emit stats and we send it to this thing that does sort of some windowing and additional statistic generation, and then send it off to disk and then off to Firefly, which produces graphs that look better than that one. So let's talk about this section. Essentially, you've got like some JSON from a log file, some data structure with information. You can send it to a Python script, which takes some data out of the JSON and maybe computes a statistic or a couple statistics. These are user scripts that basically any developer can kind of plug in and start emitting statistics for. And you get statistics out with like some key and a value and a timestamp there on the end. So then that gets sent across to essentially like a statistics aggregator, which keeps like an n-second buffer. In this case, I just did 10 seconds. And it maintains some stats for the last n seconds. We insert statistics into it, and then once in a while it goes and computes some statistics, percentiles, means, counts, 95ths, things like that, which are really easy, which are really great because it makes it easy to figure out sort of what the average performance of the website is. So how good is the homepage usually, and then how bad is it for our power users. Like if you look at 99th percentile timings, it can show you the people that have millions of friends on Yelp and have written bajillion reviews, how bad is loading their homepage. And then we shove it on disk, and then Firefly knows how to read it from disk. And you get graphs that look like that. So that's basically my talk. Any questions?
Oh, for the stack collection, do you just use the Python logging framework and write to a UDP socket, or?
Sorry, which part of it? Are you talking about this
Go back,
thing?
other
or-
slide, other slide,
This one?
more back, other. Yeah, this one, your web server. So
Yeah.
are they just writing using the standard log framework and then writing the UDP collector, or?
Yeah, so we don't use the Python logging framework. We basically wrote a small package which makes it that lets us log scribe lines. We've been using this forever, so I don't know if there are any easier or more widely adopted tools, but we basically just wrote a scribe client that knows how to pick the nearest scribe server or whatever, and then essentially ships off lines associated with the channel. I bet you could configure Python's logger to sort of do something similar, but I'm not familiar with how to do that. Any other questions?
So way at the beginning when you had a single database,
Yeah.
I'm curious, what was the bottleneck? Was it disk? Was it memory? Was it CPU?
I don't know. I mean, this was before my time. But I think that the blocker there tends to typically be either disk or CPU. I'd be willing to wager.
I wonder if, now that we have these really fast solid state drives, I'm imagining these big mainframe computers that could have a central database.
Yeah, I mean, solid state drives definitely changed databases for the better. I mean, MySQL knows how to keep some things in memory, but typically you're going to be hitting the disk for any sort of random read. We have experimented with SSDs at Yelp. I think we use them in some systems, but it's for production server hardware, things are still a little bit shaky. And I couldn't tell you exactly why, because we have a separate systems team which actually does manages hardware deployments and stuff. I haven't been directly involved with that, but I know that we've run into some roadblocks with that.
I wonder if like 10 years or 20 years in the future, all these problems like kind of go away because you can
Yeah.
have one big.
It's an interesting thought. I don't think that we'd be able to collapse our entire database cluster onto a single machine.